Hi all. In this presentation, we'll be working through a problem called Stuck in a Rut that appeared in the Bronze and Silver USA Computer Olympiad contests in December 2020. After we go through the problem description, we'll work through a few examples to make sure we understand what's going on. This problem turns out to be relatively easy to solve using a naive direct simulation, which we'll take a look at first. But as we'll see, this solution is not feasible for some of the test cases, so we'll also consider a more efficient approach. We'll finally conclude by working through an example implementation in C++. This is a really fun problem. Let's get started. Alright, so here's the problem description. Let's go through it now quickly. Farmer John has recently expanded the size of his farm. So from the perspective of his cows, it is effectively now infinite in size. The cows think of the grazing area of the farm as an infinite 2D grid of square cells, each filled with delicious grass. Think of each cell as a square in an infinite chessboard. Each of Farmer John's n cows, where n is from 1 to 50, starts out in a different cell. Some start facing north and some start facing east. Every hour, every cow either stops if the grass in her current cell has already been eaten by another cow, or eats all the grass in her current cell and moves one cell forward according to the direction she faces. Over time, each cow therefore leaves a barren rut of empty cells behind her. If two cows move onto the same grassy cell in the same move, they share the cell and continue moving in their respective directions in the next hour. Please determine the amount of grass eaten by each cow. Some cows never stop and therefore eat an infinite amount of grass. Okay, so here is the description of the input and expected output, also taken verbatim from the problem description. Basically, we are given the direction, N for north or E for east, and the starting coordinates of each cow, and we're to output how much grass each cow ate by the end of the simulation. We'll return to some of the constraints given in more detail a little later. Here we see an example of the input fed to us from standard input, along with the expected output of our program, which we're expected to write to standard output. In this example, we have 6 cows, and for each cow we are given its direction, its x-coordinate, and its y-coordinate. From the expected sample output, it turns out that the first, second, fifth, and sixth cows ended up eating grass from 5, 3, 2, and 5 cells respectively, and the third and fourth cows ended up eating an infinite amount of grass. So if you haven't tried this problem yet, why not pause the video now, try the problem, and then hit play again when you're ready to continue. Okay, before we start, let's make sure we understand what's going on. Here is a field with 2 cows, an eastward cow at 4,6 and a northward cow at 11,1. To make things easier to see, I've set things up so that Jersey or brown cows face east and Friesland or spotted cows face north. I'm also keeping track of how many cells each cow has eaten grass from as the simulation progresses. After an hour, each cow finishes eating the grass in its cell and moves to the adjacent cell in the direction it is facing, leaving an empty rut in its wake. However, if a cow reaches a rut, that is, a cell in which the grass has already been eaten by another cow, it stops. So in this example, the eastward cow stopped after having eaten grass from 7 cells, but the northward cow was never blocked and so went on to eat an infinite amount of grass. Now things can become complicated as more cows are added. Here we have the same eastward and northward cows, but there's an additional eastward cow at 9,4. This time, the northward cow has been blocked before it could reach the y-coordinate of the eastward cow in the previous example. As a result, the northward cow has stopped after having eaten grass from 3 cells, and the eastward cow that was blocked by the northward cow in the previous example now went on to eat an infinite amount of grass. Alright, now let's take a look at what the simulation would look like for the sample input given in the problem statement. Here we have the 6 cows. The first cow is facing east at 3,5. The second cow is facing north at 5,3. The third cow is facing east at 4,6. The fourth cow is facing east at 10,4. The fifth cow is facing north at 11,2. And the sixth cow is facing north at 8,1. So let's start the simulation. We see that one cow has already been blocked by a rut after 2 hours. And something interesting has happened here. We have 2 cows that have landed on the same patch of grass. If we look at the problem description, however, we see that this is fine. In this case, the cows share the cell and continue moving in their respective directions in the next hour. In other words, they don't affect each other at all. In the end, we see that 4 cows ended up stopping after having eaten grass from 3, 5, 5, and 2 cells respectively, and the other 2 cows continued on forever, which matches the expected output. Great. Now let's think about how we could solve this problem in general. A naive approach would be to model the field as a 2D array of Boolean variables that records whether each cell contains grass or a rut. We could then place the cows in their respective cells facing their respective directions and then step through the simulation using the given rules hour by hour, having the cows eat the grass as they move and keeping track of how much grass each cow has eaten, until all the cows have either hit a rut and stopped or escaped the array. In fact, this is the algorithm that was used to generate the animations in this presentation. But there's a big problem with this approach. Let's take a look at the problem description again. Can you see what the problem is? The thing is that the x and y coordinates can be as high as 1 billion. Now, even if we represented each cell in the field as a single bit, that means we would potentially need to set up a 2D array comprised of up to 1 billion squared, that is a quintillion bits, to represent the state of the field, which is not feasible. And even ignoring this unacceptable space complexity, we also don't have the time needed to iterate over as many hours as it may take on a billion by billion field to find out which cows stopped and which cows escaped. Having said that, the problem statement does say that for some of the test cases, all coordinates are at most 100. So this naive simulation-based approach might be feasible for at least some of the test cases. In any case, if we want our script to pass all the test cases, we need a more efficient approach. It turns out that, instead of iterating through each hour in the simulation, we can skip the uneventful hours and jump straight to moments where individual cows hit ruts and are forced to stop moving. Let's see how that might work. Let's first look at an example with a single cow facing north. Of course, this cow will never hit a rut and will move through an infinite number of cells. Now let's say that we have another cow also facing north. In this case, it is impossible for the 2 cows moving parallel to each other to interact unless they have the same x-coordinate. But remember, we are told in the problem description that all x and y coordinates are distinct. In short, it's impossible for 2 cows traveling in the same direction to interact with each other. Now, even if the other cow is going east, there are still some cases in which it's impossible for the 2 cows to interact with each other. For example, here we have a cow going east that has a y-coordinate less than the y-coordinate of the cow going north. And of course, it's impossible for either cow to block the other in this case. Similarly, here we have an eastward cow whose x-coordinate is greater than the northward cow's x-coordinate. Again, it's impossible for either cow to block the other. In other words, it is necessary for cows to travel in different directions in order to interact with each other, but it is not sufficient. So exactly when will 2 cows interact with each other? Of course, a northward cow and an eastward cow can only interact with each other if the eastward cow's x-coordinate is less than and its y-coordinate is greater than the northward cow's respective coordinates. Great, so that's an important thing to realize. So we've established that the eastward cow must be to the west and north of the northward cow if one cow is to block the other, but there are three things that can happen in this situation. The northward cow could block the eastward cow, like so. The two cows could share a cell at the same point in time and then continue on their way, like so. Or the eastward cow might block the northward cow, like so. So the question is, based on the initial positions of the cows, how can we determine which outcome will be realized? Let's think about that now. Here we have a northward and an eastward cow, such that the eastward cow is to the north and west of the northward cow. Let's arbitrarily look at the situation from the northward cow's perspective. We want to determine whether the northward cow will be blocked by the eastward cow. Let's say that the northward cow is initially at coordinates x0, y0. Since it goes 1 unit north after each hour, unless it is blocked, which we'll ignore for now, its y coordinate after t hours will be y0 plus t. Now let's say that the initial position of the eastward cow is x prime 0, y prime 0. Since it is moving at 1 cell per hour eastwards, again unless it is blocked, which we'll ignore for now, after t hours its x coordinate will be x prime 0 plus t. Then, the first question we should ask ourselves is, how long will it take for our northward cow to reach the y coordinate of the eastward cow? Of course, that will just be the difference between the y coordinates of the two cows. Then, the next question we should ask is, by the time our northward cow reaches the eastward cow's y coordinate, where will the eastward cow be? Well, since the time that will have elapsed by then is the difference between the two cows' y coordinates, the x coordinate of the eastward cow will be x prime 0 plus y prime 0 minus y0. And then we simply compare that x coordinate to the x coordinate of our northward cow. If it is smaller, then the eastward cow will not block our northward cow. In fact, it is the eastward cow that will be blocked. If that x coordinate is equal to our northward cow's x coordinate, it means that the two cows will share a cell at time t and then continue without interfering with each other any further. But if that x coordinate is greater than our northward cow's x coordinate, then the eastward cow will block the northward cow. So that's the basic idea. However, this reasoning so far has ignored the fact that the eastward cow may have been blocked by another cow along the way. Let's see if we can modify our reasoning to take this into account. So let's start again. This time there is a rut that will cause the eastward cow to stop at some point. Again, let's view the situation from the perspective of the northward cow and try to determine whether the eastward cow will block it. We'll start, as before, by asking how long it will take for our northward cow to reach the y coordinate of the eastward cow. Just as before, this will be the difference between the y coordinates of the two cows. And just as before, our next question is, at this point in time, where will the eastward cow be? This time, however, let's think about the answer to the question in terms of whether the eastward cow is still moving or has been stopped at some point. If the eastward cow is still moving, the answer to the question is the same as before. X prime t equals x prime 0 plus y prime 0 minus y0. But if the eastward cow has stopped at some point in the meantime, then where will it be? Well, if it stops at some point after the time t we've just calculated, then its x coordinate at time t will still be x prime 0 plus t. But if it is stopped at some point before time t, then its x coordinate will be x prime 0 plus however far it traveled before it was stopped. However, and this is an important thing to realize, by keeping track of how much grass the cow ate by the time it was stopped, we implicitly keep track of how far it moved before it was stopped. Thus, we can answer the question as follows. If the eastward cow is no longer moving, then its position at time t will be x prime 0 plus whichever is smallest, t or the amount of grass the eastward cow ate before it stopped. Now, we have only looked at things from the perspective of the cow going north, but our results are exactly analogous if we look at the situation from the perspective of the cow going east. So putting this together, we can solve the problem along these lines. We forget about modeling the field and instead only model the cows. For each cow, we need to keep track of its starting position, direction, whether it is still moving, and how much grass it has eaten. Initially, each cow has the potential to go on forever, so we'll set the amount of grass eaten to infinity and set its state to moving. Then, for each cow that is still moving, we calculate the time it would take for each other cow to block it, which could be infinity if the other cow does not block it, and keep track of the least time for a collision with a rut as we go. In other words, we are searching for the point in time when the earliest of the remaining collisions with ruts occurs. If the earliest such time is infinity, it means we are done and can break out. Otherwise, we identify the earliest collision time, stop the respective cow from moving, and set the amount of grass that cow has eaten to the earliest collision time, and then repeat. Okay, let's take a look at what this might look like in C++. Again, if you haven't tried the problem yet, you might want to try it now so that the rest of the presentation will not be too much of a spoiler, and then hit play again when you're ready to continue. Here, we define infinity using a value that cannot be encountered in the tests. And here, we create a representation of a cow. To simplify things later on, here is a method that returns the time that a given cow is blocked by another cow. As we discussed, if the other cow is facing the same direction, then it is impossible for the other cow to block this cow, so we return infinity. Next, we consider the case where this cow is facing north. Remember, in this case, the other cow can only potentially block this cow if its x-coordinate is lower and its y-coordinate is higher. In that case, we first answer the question, how much time will pass before this cow reaches the y-coordinate of the other cow? We then answer the question, what will the x-coordinate of the other cow be after this amount of time? If the other cow is still moving, then the answer is simply its x-coordinate plus t, the amount of time we calculated. Otherwise, it will be its x-coordinate plus whichever is lowest, t or the amount of grass the cow ate before it became stuck in a rut. If that x-coordinate value is greater than this cow's x-coordinate, it means that this cow will be blocked by the rut left in the wake of the other cow at time t. Otherwise, the other cow does not block this cow and we return infinity. The case where this cow is facing east is perfectly analogous. And this line is only reached if the other cow is facing a different direction, but it is impossible for it to block this cow. For example, if this cow is northward, the other cow is eastward, but the eastward cow's starting x-coordinate is greater than the northward cow's x-coordinate. And then we're ready to begin. We first read in the number of cows from the standard input. Then we read in the direction and coordinates of each cow, and add an instance of each cow to a vector of cows. And here's the simulation. For each cow that is still going, we find when it would be blocked by a rut generated by each other cow, and keep track of the cow that would get stuck in a rut first. If the least time is infinite, then we're done. Otherwise, we set the amount of grass eaten by the cow that would get stuck in a rut first to the least time, stop that cow from moving, and then continue until the time taken until the next blockage is infinite. Once we are done, we simply write the amount of grass each cow has eaten to the standard output. And we're done. And that's that. I hope you enjoyed the presentation. As always, let me know if you solved this problem in a completely different way.